Hi, Roshan. Thanks for joining. So, we would like to
Hi.
discuss about the principles to create AGI, that is Artificial General Intelligence, and pass the Turing Test. So, I'll just explain briefly
Okay.
what is Turing Test. Then I'll go on to describe what AGI means and what AI means. If you are new to AI, I'll explain in a brief manner. So, Turing test is something devised by Alan Turing, who is considered as the father of artificial intelligence. So, he devised a mechanism where the judge, the person who's asking the questions, should not know the difference between the machine and the human being. So, let's say the judge is asking questions to a Turing machine. The machine should answer in such a
Okay.
way that the judge thinks that he's a human being who is answering his questions. So the judge
Okay.
would be
So
blindfolded.
it's like
Yeah,
vote is not. It is not written or something. Understand?
yeah. So the judge would be blindfolded. He'll be in a different room or something like that, and he'll be just asking questions, and the Turing machine would be responding to his questions. And if he finds it suitable, in the sense, if he thinks that the Turing machine is answering like a normal human being, that means we have passed the Turing test.
Okay.
So now that is the objective now of all this work which we have done. And let's go ahead and see what we have got today. See, the agenda for today's discussion is what is the problem? So it starts with a problem definition. So problem definition, then solutionscape and avenues in the sense of how it can be used for further expansion, principles involved, creation of the solution and future expansion. And I'm requesting the audience and the viewers not to confine themselves and to have the free flow of thoughts. To add on this to this concept, the other day we were discussing about the thought field, right? Thought field, thought spectrum.
Yes.
Yeah. So I
Correct.
found out
Last time
something. Have you encountered deja vu? You know deja vu, right?
yeah. Deja vu.
Deja vu in the sense you tend to experience a phenomena where you feel that the such an happening is happened to you earlier. In a sense, you see someone walking, or you see the tree swaying or something. You feel that that particular event has happened in your past.
Correct. Yeah. We do get sometimes like that moment. Yes.
So
That's
that is
right.
deja vu. So how does that happen? That can that there are two definitions. There could be two reasons for it. One, the same happening has happened in a parallel universe. The same happening has happened in a parallel universe, and we are experiencing in our current universe, and we don't know how it has happened and how it is the event is transmitted from that universe to this universe is through thought waves, through the thought
Okay.
spectrum, because there is no other spectrum which could travel across universes, across parallel universes. So this would help in bridging the gap in understanding quantum mechanics, in the sense they always have this problem of this observer and measurement paradoxes. So what happens is you observe something, something else happens. You measure something, something else happens. So that's the paradox of all quantum mechanics. So now what happens is, if you bridge that with thought waves, you say that deja vu in a different universe, at that point of time, you have not observed. You're not in that universe. You're in this
Correct.
universe, but you've measured it. You've measured it through your thought. So if you extend this, and if you extend along with the quantum field, I guess we could solve the hidden aspects of quantum mechanics. So we'll discuss about that in a different presentation. So now let's concentrate on our presentation on AGI and how we pass the Turing test. And the reason why I'm talking about deja vu and thought wave is, don't confine yourself. Don't confine yourself to a predetermined approach of thought process. Now, what is the problem definition? the problem we have at hand is the existing AI systems lack generalization, as in the decision making is in new scenarios different to a great extent from the pre-existing scenarios, pre-trained scenarios is not good. See, let's say you go to a new city. You are in Bangalore. You go to, let's say, Hyderabad. You, with minimum information, you are able to traverse along the city. You are able to navigate all over the city. That's because you have a similar picture, a similar layout of cities when you have been living in Bangalore. So you'll learn that all cities would be similar. The layout would be similar. You'll get a bus in the bus stop. You'll get a train in the train station, and you. So that is all natural. So that layout, that understanding, you are there. So that is your learning. But imagine a computer or machine is going to Hyderabad. It can never do the same way which the way you have navigated. It can never navigate like you.
Correct.
It has to be fed all the maps of Hyderabad.
Yes, like even for the artificial intelligence, the model they needs to get trained.
Pre-trained.
Once model is trained, then only pre-trained, then only it works.
Pre-trained, transfer learning, and all those things. I'll discuss about that when we talk about the training procedure which we are innovating. Yeah. So pre-trained approach, programmed approach. That won't help, because let's say you have 100 smart cities in India, and you ask a robot to navigate all the 100 smart cities. You will have to feed the map of all these cities to that robot. That's not good.
Yes.
That's the tedious, time-consuming activity. So the same happens with all the housing websites. The same thing happens with all the navigation data which Google has or something. They will have to feed the data for each city. They have to do everything from scratch. So that is the normal artificial intelligence which we have currently. So imagine we have artificial general intelligence which generalizes stuff. So it's like a baby. A baby learns very fast. That's because it generalizes very fast. The baby, infant, and early childhood stage, where during that early childhood stage, people learn very fast because they generalize very well. The only reason they are not as intelligent as the scientists is that they are not able to articulate. If they are able to articulate at that young age, then they'll be equivalent to the scientists, because their learning curve is very high. So that is what we are trying to implement using our AGI systems. That was this suggestion was given by Josh Tannenbaum of MIT in a webinar, and which was broadcasted by Lex Friedman. He is a very good person in this field and expert in this field. So if you see that webinar, you will see that towards the end, Josh Tannenbaum says, you will have to think like a child, think like a baby, infant, and realize artificial general intelligence. So that is what we are trying to do, and we are trying to accelerate that learning using biological Turing machines.
Okay.
So what is the solution scape and avenue which we are having? We are using biological Turing machines built on the principles of protein synthesis. So we have the neural networks, the synaptic connections, and all those things going on for the artificial neural networks which we have, and convolutional neural networks, and other for deep neural networks. It all uses the synaptic connections and the input, output, and hidden layers. And the number of hidden layers you have, the more number of hidden layers you have, the more deep is your network. So this is a pretty simple construct, just a 3-layer construct. But if you go for protein synthesis concept, you will have 6 layers. You will have 6 elaborate layers, and 3 basic functionalities. One is DNA to mRNA, mRNA to amino acid. So DNA to mRNA is transcription, mRNA to amino acid is translation. Yeah. So this is the process. Now, we have this concept of phenotype variation. Phenotype is gene expression. So let's say why is the eye color of some people are green, some people are blue, some people are black, brown, and other things. That's a phenotype variation. That's a gene expression. That's due to environmental factors, genetic factors. Less genetic, more environmental, you could say, phenotype. But eye color is not a good example. There could be other factors like lifestyle, lifestyle and nutrition based genetic factors, and your health. So that is like a phenotype expression, you could say. That's a phenotype variation based on your environment. So less of genetic impact and more of environmental factors. So there comes this field of social epigenetics as well. Social epigenetics is exactly that. So you have good vibes. You have good vibes in your environment. You are doing good. Your body feels good. Your health is good. So that is vibes and social epigenetics, and phenotype expression is also part of it. So now this phenotype variation happens when there is a transcription error. So what happens is from DNA to mRNA, when there is an error, even God does errors. So the natural process, even there are errors in that process. So that is an advantage for us. Why it is an advantage? You have variation.